Okay, in this talk, I will explain how we capture exact measures of evaluation in calculus interpreting classical logic. This is joint work with Delia Kesner. So we will use the intersection types, which were introduced by Copo and Desani to give meanings to more terms. So in an intersection type system, you should have T is typeable if only if terminates. So intersection types have had various purposes. For instance, Kobayashi and Hong have used intersection types to simplify Hong's proof that monadic second-order logic is decidable. A bit later, Gardner and Daniel de Carvalho introduced non-idempotent intersection types, which bring quantitative information on terms. So these types were used in complexity analysis, for instance, by Terui and Simona Ronchi della Rocca. Recently, Bernard et Langrand and Akatoli, Kesner and Langrand have used and refined non-idempotent intersection types to obtain exact measures of evaluation, that is the evaluation length to the normal form and the size of the normal form. On the other hand, Michel Parigot introduced the lambda mu calculus, which is a computational interpretation of classical natural deduction. Thus, it enables expressing control operators and doing backtracking. The lambda mu calculus is an extension of the lambda calculus, with a new reduction called mu reduction. And in the lambda mu calculus, we'll also have covariables, which are called names. So, since non-idempotent intersection types allow capturing exact measures of evaluation in the intuitionistic case, one may wonder what happens if we add control operators. Well, the contribution of this talk is proving that there is a type system for the lambda mu calculus such that T evaluates to a normal form T prime of size F in L beta steps on M mu steps, if only if we have this kind of annotated judgment with L, M, and F. And we'll do this for three evaluation strategies: head evaluation, leftmost, outermost evaluation, and the maximal evaluation, which computes a reduction sequence of the greatest length. So here are the main ingredients of our solution. We'll distinguish between persistent elements in a term, that is the ones which remain in the normal forms, and the consuming ones, which are used during reduction. So in this term below, you see that the abstraction, the variable, and the application of the redex are consumed, so that they are in red. Whereas y and z will remain in the normal form, and they are in blue, they are persistent. To make this distinction formal, we will use a new type constructor, a persistent arrow, and a new type constant bullet that will assign to anything that is not applied. So typically, the persistent arrow won't be assignable to an abstraction, because an abstraction creates a redex when we apply it. But we may type, when we don't use an abstraction, we may type it with the bullet. And to type the variables of normal forms, we will use persistent arrows, since the application of normal forms do not disappear. The problem is that this distinction cannot be formally done in the lambda calculus or in the lambda mu calculus. For instance, if I consider lambda x applied to the identity I, the identity is duplicated, and one copy of the identity is consuming, the other one is persistent. So was the initial identity persistent or consuming? It's not possible to say. So the idea is to use non-idempotent types. Non-idempotent intersection types allow to linearize terms, that is, to create copies of terms or subterms before they are duplicated. So for instance, the term on the left becomes lambda x applied to the multiset of I on I, so that we have one I which is persistent and the other one which is consuming. In the lambda mu calculus, since we will deal with control operators, we'll need to manipulate and actually to transform persistent arrows into consuming one. It's related to the fact that, as we will see, mu reduction will create applications and will bring new cases of redex creation. So I will explain how the lambda mu calculus work. So it's well known that Peirce's law gives classical logic. And in 90, Tim Griffin noticed that call CC could be typed with Peirce law, which proved that Curie-Howard could be extended to classical logic. So first, classical logic corresponds to backtracking from the computational point of view. Just after that, Michel Parigot introduced the lambda calculus, which corresponds to classical natural deduction. And it features judgment with several formulas on the right-hand side of the sequence. So this is Peirce law. This derivation is classical only because we have two formulas on the right-hand side of the derivation. The lambda calculus corresponds to a focused form of classical natural deduction. So we have an active formula and several inactive formulas on the right-hand side of sequence. And we may activate and deactivate formulas in sequence. This gives the lambda calculus, which is an extension of the lambda calculus, plus names, which we will use to store inactive formulas, and two new constructors, the naming and the mu abstraction, so which correspond to deactivation and activation of formulas. It exists in a typed and in an untyped version. So in the simply typed version, we have strong normalization. The operational semantics of call CC can be represented by this lambda mu term, which has Peirce law, as expected. We have a new kind of reduction, which is called mu reduction. When the mu abstraction binds alpha, all the terms V which were named with alpha will be fed with the argument U of the derivation. Thus, mu reduction creates application, and we will explain why in the next slide. So, in the lambda calculus, we have usual beta evaluation steps. Just look at this. We have an abstraction followed by an application rule, exactly like in the lambda calculus. But we have a new form of redax. So here we have an application, but the arrow A arrow B doesn't come from an abstraction, but it comes from the activation of the arrow. So this arrow was probably deactivated before, possibly in several places. So how do we perform a cut here? We'll actually take the argument derivation typing S with A and put it inside the derivation, like this. We notice two things. We have created application inside the derivation, and instead of saving A arrow B, as in the left-hand side, we now save and deactivate B. So first, we have creation of application rules, and this explains the form of mu reduction in the previous slide. So now I will explain the basics of non-idempotent intersection types. So we consider this reduction sequence. Notice that the I in reds are consuming, they are destroyed during reduction, and the ones in blue are persistent. I will type I. So because it's simply typable, whereas the term on the left-hand side is not. So I consider F equal to O arrow O, so that I may define this derivation typing I applied to II. Now I will type the term on the left-hand side using intersection types. So basically, intersection types allow you to assign several times to the same variable. So for instance, when X has type A inter B, it means that X has both type A and B. And in the non-idempotent setting, the number of times that you assign a type matters. So when X has type A inter B inter A, it means that X has type A twice and type B once. And thus, in the non-idempotent setting, we may just write multiset A, B, A instead of A inter B inter A. Since I may assign several types to X, I can use it as a placeholder for I. I may now compute environments. So to compute the environment of XX, I just need to look at the types that I have assigned to X above. So I have two axiom rules. It means that X has been assigned F arrow F and F. Likewise, I can compute the environment of XXX. I look at the axiom above. I have F arrow F, F arrow F, and F. Now, when I perform the abstraction, I collect all the types assigned to X. I have a quantitative information. X has been typed twice with F arrow F and once with F, and it is seen in the multiset. Now, since the domains of the function type is of cardinal 3, I must type the argument I 3 times. I is equal to lambda y dot y. So 2 times with F arrow F and 1 time with F. And I may conclude the derivation now. Actually, I was able to perform subject expansion because I had the right to assign several types to F. This is a really important point. Now, let us explain why, in the non-independent setting, derivation decrease under evaluation. So this is a situation of before. X has been be typed twice with a type A1 and once with a type A2. So that actually the argument needs to be typed exactly 3 times. And to perform reduction, I will just replace the axiom rule typing X with argument derivation. And you notice that I did not need to duplicate anything, so that the size has decreased. And thus, non-dependency ensure a decrease when we evaluate terms. So here is the system defined by Philippa Gardner and De Carvalho. So a type is either a type variable or an arrow whose domain contains several types. So let's look at the rules. The axiom rules is relevant. We don't have weakening. You notice that in the left-hand side of the axiom rule, we only have a single-term multiset. We do not assign to X any unuseful types. In the application rule, the domain contains several times sigma I, and you must type, as many times as there are sigma I. We have non-idempotency, so we have accumulation of typing information like this. An important point is that we may type in a normal form the argument several times. So here are 3 typings of X, Y. One on the left, Y is typed once, then it's not typed, and then it's typed 3 times. Notice, however, that on the left-hand side of applications, things are always typed. So the head regex is always typed. The main properties of the system. We have subject reduction, but also subject expansion, which is specific to intersection types. We also have a decrease, which is specific to non-independent intersection types. It decreases the size, which is the number of adjustments that contains a derivation. And we have a characterization theorem. T is typeable if only if a derivation terminates, if only if there is a reduction path of an unspecified form from T to a head normal form. The decrease gives us actually upper bound. The size of the derivation is greater than the sum of the evaluation length plus the size of the head normal form. And the characterization is proved like this. Using the subject reduction and decrease, we prove that if T is typeable, then head evaluation terminates. And typing head normal forms, which can be done only by a simple induction, and using subject expansion, we prove that when a term is normalizing, then it's typeable. Last, we have an equality when pi is minimal in some sense. This actually adapts for the lambda mu calculus, but since we have names which are covariables, we need to consider the dual of intersection types, that is non-independent union types with angle brackets. We have the nice properties of non-independent types, so accumulation of typing information. The typing of call CC becomes the one on the left-hand side. And the application rule will be based on a generalization of modulus. We consider a disjunction of implication instead of just one implication as in the lambda calculus. The problem is that mu reduction may increase the number of nodes. It's because of the creation of application rules. So if you want to obtain a decrease, you need to take into account several things. And the most important thing is to take into account the arities of functions that you deactivate. And first, our previous contribution was to give a quantitative characterization of head and strong normalization in the non-lambda calculus with upper bounds. So how do we capture exact measure? Well, remember that we want to distinguish between persistent element and consuming elements. So we will use a new type constructor, the persistent arrow. and it will help us define exact types, which are actually the ones which capture exact measure. So here is our new grammar. So we have two kind of arrows now, and we have the subclass of exact types, which is defined as this. And we say that a judgment is exact when its type is exact and all the types in the context are also exact. So typically, I should type a normal form like this. So notice that the domain of an exact type is of cardinal 1. So arguments are always typed once. They are not untyped. They are not typed twice. They are typed once. So, moreover, I will have a special abstraction rule which allows me to type abstraction with the bullet, which is not an arrow type, as long I won't use this abstraction, which is the case in a normal form. And of course, all this thing works only if I've been able to inductively type the normal forms U1 and U2 with bullet. And this will be possible thanks to the special abstraction rule. Actually, it works when I want to compute the full normal forms, for instance, with the leftmost, outermost evaluation. But if I want to compute a normal form with the evaluation, I don't want the arguments to be typed. So I need to redefine exact types. So instead of considering the singleton domains, I will consider empty domains. And this will give me this. And in this new derivation, you notice that the arguments are not typed, which is what I was expecting. So now, the real system. I want to have, for the lambda calculus, I want to have annotated judgment with L and F, L being the number of, for instance, head evaluation steps to head normal form, and F, the size of the head normal form. And the main idea of this rule is that by counting consuming arrows, I will obtain the evaluation length L, and by counting persistent arrows, I will obtain the size of the head normal form F. I will discuss the rules briefly, but the slides will be on my page. So axiom rules, a variable is a normal form of size 1, so nothing much to say. Consuming abstraction, the one that are used in redexes. Well, there is this rule. Just look at the definition of L. We increase L by 1 because since in non-independent settings terms are linearized, an abstraction will be used exactly once and no more. For persistent abstraction, we have this rule. I skip the details, but it means that we obtain the type bullet for an abstraction at the end, and it doesn't change the number of evaluation steps since it's not used. We have a unique rule for application rules, whether they are persistent or not. So actually, I need to know if the application will remain in the normal form or not. So if you see this definition in blue, so for instance, when I type the normal form x, the term xu, I have a persistent arrow, so then I know that the application is persistent. I will add 1. But if I look in another case, when I have a redex, the arrow cannot be persistent, and so it's consuming. And since the arrow is consuming, I won't add 0 to the size of the. I won't add anything to the size of the normal form. It will be destroyed. Now let's look at the former term. So we typed lambda xxx applied to I in this way. If I want to obtain an exact typing, I won't type the persistent identity with O arrow O, but just with bullet. It will first give me this. So we will just look at this part. So I still have 2 applications which are typed in the usual way. If I compute the counters, I obtain 1, 0. 1 means that I use these identities once, and 0 means that they will be completely destroyed so that they don't contribute to the normal form. And the persistent identity is now typed with bullet. And the counters will be 2, 0, 2. 0 because it won't be used, and 2 because lambda, the identity is a term of size 2. I could compute the other counters, and the initial term has counters 3, 2, and actually it's because it reduced to its normal form in 3 steps, and its normal form is of size 2, as expected. So in the lambda calculus, still, we define exact derivation as derivation that contain only exact types in their conclusion. So we don't need to look in inner judgments of derivation. We have this characterization theorem in the case of head evaluation and leftmost outermost evaluation. So we obtain the exact bound as expected. And it may be adapted to the maximal reduction strategy. The maximal reduction strategy is like the leftmost outermost reduction strategy, except that it will never erase an argument unless this argument has been computed to a normal form. So for that, we need to force erasable argument to be typed. And actually, the statement is a bit modified. We'll see that later. We must take into account of the size of all the normal forms we may have erased during the maximal strategy. Now the case of the lambda mu calculus. So we have union types. So we must also define exactness for intersection and union types. So this is important in these rules. We consider the free strategy head, leftmost, outermost, or maximal. And actually, the two important rules are the new ones for naming and mu abstraction. So for command for naming, just means that when we use the name alpha, we'll store in alpha the type of the term using the non-independent union operator. The most subtle point is the mu abstraction. So actually, when we perform mu abstraction, we will activate with the up arrow the type of alpha. It's too difficult for the time, so I point you to the section 3.3 of the paper. So what does it do? It just transforms persistent arrow into consuming one. It's the main subtlety compared to previous systems for the lambda mu calculus or for lambda calculus, because usually mu abstraction will never change the type that it tries to restore. So this point is in section 3.3. Moreover, we have various counters. So the arity, which will help us count how many times this type of mu abstraction is used. And we have seen that mu abstraction may create application rules. Some will be destroyed, some will be persistent. And the counter CP of U allows us to count the persistent application that will be created. It's defined like this. We count two top-level persistent arrows. So we obtain our main theorem. So we have a parameterized system. It depends on two things. We define exact types so that we say what kind of normal form we compute, whether it's head normal forms or full normal forms, as in leftmost, outermost, and maximal evaluation. And we also say if erasable arguments should be typed. It's important that erasable arguments are typed when we try to capture exact length for the maximal evaluation. But it's not important when we consider an and leftmost outermost evaluation. And we obtain our theorem. So the type system for the free strategy captures L, the number of beta steps, M, the number of mu steps, and F, the size of the normal form. But in the case of maximal evaluation, we should take into account E, which is the size of all what has been erased during maximal evaluation. And we have a parameterized approach. So if you look at the long version of the paper, you will see that the proofs are comparatively very short. Now, I will finish here. So let's remember the main idea. Non-idempotency is about forbidding duplication for typing derivation. It brings a very simple operational semantics and simple proof of termination. And actually, termination, because of the decrease, will bring us quantitative information about terms. To obtain exact bounds, we refine the non-idempotent setting by distinguishing between persistent and consuming element. And it will give us evaluation length and form of the size of the normal form. And last, to deal with classical operators in non-binary calculus, we need to activate persistent errors. So for future works, we'll try to study callback p-value on the lambda bar mu multi. Thank you.